This video will be looking at the Walding in-text questions for Chapter 10, starting with question 10 and going through to question 19. So first question reads, a 50-gram copper mass is heated by placing it in boiling water. It is then placed in a beaker containing 250 grams of an unknown liquid at 20 degrees Celsius. The final temperature of the weight in the liquid is found to be 25 degrees. What is the specific heat of the liquid? And we're assuming no heat is lost to the surroundings, so we're pretending that it's going to be just the heat transference between this liquid and this copper mass. So let's start off by thinking about what are our unknown variables here. So we're told that there is the mass of copper, which equals 50 grams, 0.05 kilograms. And we're told the mass of this unknown liquid, I'm going to use U for unknown because my L's and C's look very similar, I've noticed, is 250 grams or 0.25 kilograms. We're told that there is a change of temperature, or we can infer that there's a change of temperature. So we can write out the two variables themselves. Let's do that. So the temperature initial of this unknown liquid is 20 degrees Celsius. And the temperature final of this unknown liquid is 25 degrees Celsius. So we can see that the delta for our liquid must be equal to 5 degrees Celsius. It's gone up. And we're told that the temperature final of the copper is 25 degrees Celsius as well. So some things we want to know, well, what is the temperature initial of the copper? And we're going to need to know, well, we're dealing with copper, which is a known thing, so we should be able to find the specific heat capacity of copper. That one's easier than the first one, so let's do that first. We scroll back, we see that on page 245 we've got our specific heat capacities. So copper is 390 joules per kilogram Kelvin. So 390 joules per kilogram Kelvin. Great. So what's this temperature initial of the copper? So if we read the question, it says that the copper mass was heated by being placed in boiling water. Okay, so well, what's the temperature of water, or boiling water? We know the boiling point of water is 100 degrees Celsius. So it's reasonable to infer that the copper is at 100 degrees Celsius. It's been heated up by being immersed in this value. We know that two things will reach equilibrium, so if the water was continually kept at that 100, then the copper must eventually reach that 100. So again, we can calculate the delta for our copper as being minus 75 degrees Celsius. And the question is asking us, well, what is the specific heat capacity of this unknown liquid? So now we've got all our things in here. We've got our masses, we've got our deltas, and we've got a specific heat capacity of one of our substances. We are looking at a calorimetry type question here, or a thermal equilibrium question. There is a worked example right above it on this, so that's another big clue in this case. But we're looking at the heat that the copper must lose must be that the heat that the unknown liquid gains. So we could write that as a statement: the loss of energy in the copper will equal the energy gained by this unknown liquid. And as we know that change in energy is Q equals MCAT, then we can say that the subtraction, don't forget your subtraction, of MC delta T, and all of that was copper, equals MC delta T. All of that is our unknown liquid. And now we're just dealing with substituting and solving. Alright, so we've got here that, well, MC delta T, so we're going to have negative 0.05 times 390 times negative 75 would equal 0.25, I'm just putting that on a second line so I don't run off space over here, times C, that's what we're trying to find, or Cu, times 5. And from here we can rearrange, so I'm just going to solve the left-hand side first. Grab my calculator. The negative times the negative will cancel, so I'll have 0.05 times 390 times 75, and I will get 1462.5 equals, let's see, 0.25 times 5 would be 1.25 Cu, and to get that over, we'll divide by 1.25, So C equals 1,170 joules per kilogram Kelvin. And sometimes with these sort of things, it's always good to identify. We could use this as an identification. If we go back though, we don't have anything that's anywhere near 1,000 on our liquids. Okay, so it could be a mixture of a couple of liquids. Maybe it's water and maybe a bit of mercury, I guess, or maybe water and a lot of sodium chloride. That would drop it a little bit, but there is nothing there that matches that. So in this case, nothing to infer off of it. Okay, let's go to question 11. A 1500 watt jug, the electric jug is used to heat 500 milliliters of water. Calculate the time for the jug to raise the temperature of the water from room temperature to boiling point. And while we haven't covered power realistically in this in terms of what the definition is, we've got a bit of an explanation there. So 1500 watt means it supplies 1500 joules of heat energy every second. And reminded here that the density of water is 1,000 kilograms per meter cubed. Now, water is really easy in this case, that if it's 500 milliliters, it's 0.5 grams. We don't need to worry about any, so 0.5 kilograms. We don't need to worry about any weird conversions to get to it. It's pretty straightforward, just convert straight over. Everything else though is not. You could have 500 ml of ice and it's not going to have the same density as water, because remember it floats, and so it's not going to have the same mass as the same volume of water. You could have 500 milliliters of air and it's not going to have the same mass as 500 milliliters of water. So for other substances you will need to go through density and volume to convert it. Okay, so just as a quick note, I'll place this here. Volume, density, and we give it a symbol rho, is equal to mass divided by volume, and power in this case, because it's something that's going to need power, given symbol P, is equal to energy divided by time, and energy could be any of our energies. So Q in this case, it could be kinetic energy, it could be gravitational energy. It doesn't matter what it is, it's just energy. Okay, so that might be something to keep in mind for later. Maybe jot that down. Okay, so let's go to question 11. Let's look at our variables. We're told that the power is equal to 1500 watts, or 1500 joules per second. We are told that the mass, well, the volume was 500 milliliters, so the mass is going to be 0.5 kilograms. We know it's water, so the specific heat capacity of water equals 4,200 joules per kilogram Kelvin. And we want to know how to go from room temperature to boiling point. So temperature initial equals 20 degrees. Temperature final is boiling point, which means 100 degrees. So change in temperature equals 100 degrees. Sorry, change in temperature will be 80 degrees. Don't know what I was thinking then. Alright, and we've got an M, we've got a C, we've got a delta T. We're dealing with a Q equals MCAT here, and because we've got Q and P, we can then work out time from that afterwards. So, let's just work out the energy needed to raise the water, and then we can think about it logically after that. So, Q equals MCAT. Q equals 0.5 times 4,200 times 80. And so we're going to get 1,680 joules. So that's how much energy. Now power is basically saying I'm going to give this many joules every second, and I need to go up to this many joules. So we want to know how many groups of this fit into this. And if we rearrange that, we'd see that, we take the energy, if we swap these around, we'd get energy divided by power would give us time. So energy over power gives time. You can rearrange it yourself just to confirm. So we take our answer, so power, or time in this case, sorry, time will equal Q over P equals 16800 over 1500 gives us 112 seconds. And if you've ever had to boil a cup of tea for parents or perhaps yourself, I mean, that's just under 2 minutes. That's pretty reasonable for just a single massive cup of tea. Right. Question 12. In an experiment, 500 grams of copper at 80 degrees Celsius is dropped into 1 kilogram of kerosene at 20 degrees Celsius. The mixture reached a temperature of 25 degrees. What is the specific heat capacity of kerosene? Well, this question is exactly the same as that question from before. The masses are different, the initial temperature is different, the final temperature in this case is actually the same. So it's the same strategy we're going to use before. So in this case I'm going to just do our variables quickly. M copper equals 0.5 kilograms. M kero equals 1. C of copper from before, we remember, should be 390 joules per kilogram Kelvin. The change in temperature of copper will be, well, it started off at 80, went down to 25, so that's going to be negative 55 degrees Celsius. And the change in temperature of the kero went from 20 to 25, so that's 5, demented looking at 5, that's 5 degrees Celsius. And we can see we've got everything we need there, so let's substitute. So minus Q of the copper equals the change in heat of the kero minus MC delta T of the copper equals MC delta T of the kero, and if we do our substitution, minus 0.5 times 390 times negative 55, and the two negatives we can see will cancel, equals 1, so that we can ignore, times C times 5, and let's put those in. We're going to get 5 times 390 times 55, 10725, divide that by 5 because that's over there, equals the C of kero, 2145 joules per kilogram Kelvin. Don't forget your units. Okay, let's scroll down, let's find the next set of questions. Question 13. Find the energy required to melt 2.5 kilograms of gold at its melting point. So in this case we just want to know if gold is at its melting point, what's it going to take to make the gold at that temperature all transition to liquid. We don't need to know what the melting point is. We don't need to know how much energy is being given to it. We just want to know, well, what's going to cause it to do that phase change. And we know the formula for a phase change is Q equals ML. We're asked to find that Q, we need these two numbers. So the M of gold, we're told here, is 2.5 kilograms. Right, nice and easy. But we need the latent heat. Now, which latent heat do we need is the question. Now we're talking about melting, okay? And melting is the opposite of freezing. So we're looking for the latent heat of fusion, not the latent heat of vaporization. Remember, as I said, you need to know those words and be comfortable with either reversing them, because your table might not have as a heading the word that you're used to. And we're told for this one, the latent heat of fusion for gold is 6.3. Put F for fusion, or we could put, so you could put LF or you could put LM for melting. Either would be fine. 6.3 times 10 to the 4 comes from the textbook, and that's, well, yeah, joules per kilogram. And the kilograms will cancel, we'll be left with joules. We can see it's just going to be a simple straight up substitution. Q equals 2.5 times 6.3 times 10 to the power of 4 equals 2.5 times 6.3 times 10 to the power of 4 gives us 157,500 joules. Okay, question 14. A copper has a melting point of 1083 degrees Celsius. Find the energy required to melt 200 grams of copper originally at room temperature of 22 degrees. Okay, so now we've actually got to think about getting up to this point before we even make a change, and we want to melt it all. So we're saying to go, well, we've got to heat it up, and then we're going to turn it into a liquid. So there are two aspects of it in this case, so we've got to think about both. Just double checking. Yep. Yeah, textbook is rounding off a little bit with these, but I would accept these answers like this. So let's have a look. We've got, let's list off our things. We've got a mass of 200 grams, so mass of copper equals 0.2 kilograms. We are told that it has a original room temperature of 22 degrees, Ti equals 22 degrees Celsius, and it's copper, and the C of copper is 390 joules per kilogram Kelvin. Now there's a couple of other numbers in there, we'll get to that in a second, but let's think about the story here. So that we're adding this heat, and when we're first adding this heat, it's only 22 degrees, so we're going to heat it up, and that means that it's going to be part of our Q equals MCAT. That would be the first part of this story. It's being heated up. Well, what's it heating up to? We're told that it melts at 1083 degrees Celsius. So our final temperature must be 1083 degrees Celsius. So our delta T equals, well, what's the difference? We're going to get 1061 degrees Celsius. Well, we can see here now we've got mass, we've got C, we've got delta T. Well, we can work out the energy to raise it to melting point. And well, what happens after that? Now it's going to start to melt. It's going to go through that phase change, and that's going to be Q equals ML. We've got a mass, we just need our latent, and that's copper. It's a property of copper, so we just need to look it up from our textbook. If I go back to page 248, we find copper. L, the latent heat of fusion, because we are melting it, is equal to 2.05 times 10 to the power of 5 joules per kilogram. So now we've got everything. Now you could work this a couple of ways. You could show the working out for this, or you could just put it all together, because they're still just Q's, and so if we add the Q's together, the answer is still going to be the type of Q. I'm going to go with that way. So I'm going to say that the change in energy is equal to MCAT plus ML. We can see we've got a mass in both, so we can say it's M C delta T plus L. Let's substitute. Mass was 0.2, C was 390, delta T was 1061, and latent heat is 2.05 times 10 to the 5. Now, like 390 times 1061, 390 times 1061 is 3,900. No, my calculator managed to miss the multiply sign. 61. Sorry, is 413,000, so 4 times 10 to the 5. That's almost as much energy as it took to melt. It means twice as much energy as it took just to melt it, not to raise its temperature, but just to melt it. So we can see that unless we're doing a massive temperature change, with these sort of phase transitions, a lot of the energy comes from this latent heat of fusion or latent heat of vaporization. So just keep that in mind as you're going through. So we've got that, and now we need to add. Do be careful with stuff like this. Your answer, because this was say 400,000 and this is 200,000, so your answer should be around 600,000. But if you do that equals plus and then times that, if you don't make sure that it's putting these two together, you'll get that times that plus that, which won't do anything really, and then you'll multiply by 10 to 5, and you'd end up with somewhere around 10 to the 10, 10 to the 11, instead of 10 to the 5-ish. Okay, so do be careful with that. Times 10 to the power of 5, there's bracket, equals, and then we want to multiply that by 0.2, equals 123,758 joules of energy needed. Okay. Question 15. A 2-litre bottle of water at 20 degrees Celsius is placed in the freezer of a refrigerator. How much heat must be removed by the refrigerator to freeze this water? So not only do we want to lower the temperature in this case, but then we want to go through latent heat diffusion again. So it's another phase change question, just the same, but instead of adding the heat energy like we did here, instead we're going to take away the heat energy. It's not really any different, but you will need to be careful with these values, your L values. Here it was positive because I wanted to add energy to it to make it melt. For this one, my L is going to be negative because I want to take away energy to make it freeze. So you've got to be careful with that. If you're not certain, think about the story, think about the context of the situation to help you use a bit of common sense for that. So let's put this down. We've got that's originally 2 litres of water, so that means our mass must be equal to 2 kilograms. Remember, it's water, only works for water. We've got our initial temperature, so temperature initial equals 20 degrees, and we're wanting to go to freezer, to freezing point. What's the freezing point of water? 0 degrees Celsius. So therefore our delta T equals negative 20 degrees Celsius. We know the specific heat capacity of water is liquid water. We don't care about the ice phase. We're just dealing with the water phase, joules per kilogram Kelvin. And we want to know, well, what is the latent heat of fusion of water? Because just like this, we're going to need a phase change. And if we scroll up, latent heat of fusion for water, fusion meaning freezing, is, we're doing a negative, so negative 3.34 times 10 to the power of 5 joules per kilogram. Okay, so it needs to take out that much energy in order to freeze it off. So this time I'm just going to construct a little bit differently to show you a comparison. So let's do the cooling down bit first. So delta Q equals MC delta T equals 2 times 4200 times negative 20. So 2 times 4200 times 20 gives us negative 168,000 joules. Okay, it's negative, which means we're losing energy. That makes sense. We are freezing. Second bit, delta Q equals ml equals 2 times. Now here's the thing, the textbook, in terms of the reference sheet, has this as just a positive number. So if you were to do this, let's do this with positive first, 3.34 times 10 to the 5. Now, you chuck that in, 3.34 times 10 to the 5 times 2 gives us 668,000. Now, the number is right, the size of it is right, but the direction of it is wrong. Okay? So if you just chuck it in like this, you have to realize to yourself that, well, this is a negative. We're freezing it, we're taking this energy out. Because if you added this plus this, you'll get an answer of positive 500,000. Now, we don't add energy to something to make it freeze. We take energy away to make it freeze. So you've got to be careful with that. You've got to recognize to yourself, oh, this is an energy loss because I'm freezing it. It's not an energy gain. That would be if it's melting. Now, sometimes you might put negatives at the constant and make sure it's being used appropriately, and that'll work. Other times, and other people might prefer to go, alright, well, I'll just do the math like this and go, well, this must be a negative because it is a removal, and write it afterwards as 668k removed, or it's negative 668k joules. So I'm going to put the negative in here. And now we can add these two together. So then we've got negative 168,000 take away, or plus negative 668,000, and adding a negative is the same thing as just subtraction. So we end up with an answer of negative 836,000 joules. And we can see in terms of proportion, most of that came from the freezing period. Not a lot actually came from the cooling down, even though water has a much higher specific heat capacity than most substances. In this regard, it was still mostly the phase change that took out the energy. Okay, question 16. A child wanting to make a cordial ice block places 200 grams of cordial at 25 degrees in the freezer. If the freezer can remove energy at a rate of 25 joules per second, what time will it take for the cordial to freeze? Assume the specific latent heat and specific heat capacity of cordial are the same as water. So we've got the same numbers as before, we don't have to look up anything new for that. So let's start listing our variables. We're told that mass equals 200 grams. We are told that the initial temperature equals 25 degrees. And we're just going to freezing. There's no mention of another variable, another value, so we just assume freezing equals 0 degrees Celsius. So therefore delta T equals negative 25 degrees Celsius. And we're told that the power, because it's joules per second, is 25 joules or 25 watts. And that'll come into the second half of this question. Now we're dealing with water, so let's list off our values. We know that the heat capacity of water, put a C there, is equal to 4200 joules per kilogram Kelvin. And we now know that the latent heat of fusion of water was, let's just scroll up, 3.34 times 10 to the 5. Because we're freezing something, let's slap a negative out the front. Same process as before, this power bit's not going to come in till later. So let's just solve as before. So delta Q equals MCAT plus ML equals M outside of C delta T plus L. Substitute 0.2 times C of water was 4200 times T was negative 25 plus, and that L is going to be negative 3.34 times 10 to the 5. Let's solve that. 4200 times 25, negative 25, sorry, take away 3.34 10 to the power of 5, and then multiply that by 0.2, we get that the negative should be about 87.8 thousand joules of energy. But the question is asking us how long will it take? Right? And we're told that the freezer can remove energy at the rate of 25 joules per second. Like before, we've got energy divided by power, we're going to get time. So if power equals energy over time, then time equals energy over power equals 878.00. I'm not putting a negative there because all we care about, the time can't be negative. Time in this case is going to be positive. I mean, if we establish that power was negative 25 watts because that's the rate of energy removal, then a negative times a negative makes sense. So maybe if we change that to a negative in this case, then we can persist that negative through. It's still going to cancel. I mean, the negatives didn't matter in this regard, but sometimes people like to have it there. 78,000 divided by 25 is 3,512 seconds. Let's make that a little bit more contextualized for ourselves. Equals 58.5 minutes. So almost an hour to cool down or freeze our lovely little icy blocks, okay? Got to wait longer than I thought to get ice poles. 17. Okay, two ice blocks of mass 20 grams are each placed in 500 grams of water at 40 degrees. What will be the final temperature of the mixture? Assume no heat is lost to the container or the surroundings. So now we have a a thermal equilibrium thing with a phase change. So we've got to use both ideas. Now, there are a couple of ways of tackling this. The first is to do a set of questions. Say you can do 2 stages. You can go, okay, well, let's melt the ice first, and then see what the change of temperature is of the water after that, and then you'd have 0-degree water of a certain mass plus whatever the water cools down to of a certain mass, and then do thermal equilibrium like we've done before. But we can do it all in one step. I'm going to show it for this one. I've shown you the other way in class, and use whichever you prefer. So first off, let's write our variables. So we're told that there are, for ice, we have the mass of ice equals 20 grams, but there are 2 of them, so we need 40 grams, so 0.04 kilograms of ice. We are told the mass of water equals 500 grams, 0.5 kilograms. We don't know the initial temperature of the ice, so we're going to have to assume here temperature initial of ice is 0 degrees Celsius. Okay. And the temperature final of the ice is don't know, but it does equal the temperature final of the water. The temperature initial of the water equals 40 degrees Celsius. Okay. Now, the ice doesn't have to heat up before it phase changes, so that's good. We know that the C of the water equals 4200 joules per kilogram Kelvin, and the C of the ice when it turns into water, so the C is the ice, or I'm going to put L for liquid next to it, is also equal to 4200. Now you might go, wouldn't that just cancel? And the answer is no. It would if we did it piece by piece and did the phase change and then cooled it, and then we looked at the water and water together, and then that would cancel. But we're going to do it all in one go, so I do need it in there this time. And because we're dealing with a latent change, we need the latent heat of fusion for our ice, and that was 3.34 times 10 to the 5. 3.34 times 10 to the 5. Okay. And we'll see we might need a negative in front of that. I'll think about it in a second as we go through. So, how would we write this all out as 1? Let's just double check our masses, temperatures. Yep. Okay, great. We've got everything we need. So let's write the story. The loss of energy in the ice is equal to the gain in energy in the water. So the gain in energy in the water is pretty straightforward. It's just going to be Q equals MCAT. Okay. Sorry, I've got my losses are in the wrong way there. Is equal to the gain in energy of the ice. So this will be positive because it is melting, and that would be water. Okay. So the drop in energy in the water, that's straightforward. So negative MC delta T, and that's all for water. But what's happening here on the ice? So first off, it's going to gain energy and it's going to go through a phase change, and then if there's any energy left over, it's going to go through a heating period. Okay. Now the masses will be the same, so negative ml delta T of water equals, so let's factorize the m out, m inside of L plus C delta T, and that is all of ice. Now we're ready to start substituting. I can expand these delta T's and we'll get to that in a moment. Let's put our constants in and see how we go. So the mass of the water was negative 0.5 times the specific heat capacity of water times delta T of water equals the mass of the ice was 0.04 times the latent heat, which was 3.34 times 10 to the 5, plus 4200 times delta, let's just move it over a little bit, delta T of the ice itself. Okay, let's get rid of some of these numbers here. So we've got half of that, that's just going to be negative 2100 and this in this case is going to be TF, which we don't know, take away TI, which we did, and TI of water was 40 degrees. Okay. Equals 0.04 outside of 3.34 times 10 to the 5 plus 4200 outside of, let's move that over a little bit more, the initial temperature final, which we don't know, minus 0. So that's first bracket, second bracket. Let's keep tidying this up. I'm going to move this number here over first, just so that I can get this with this, and then we will have to see what we've got. Then I'll have to start expanding, I reckon. So 2100 divided by 0.04 is negative 52,500 outside of TF minus 40 equals 3.34 times 10 to the 5 plus 4200 TFs. Okay, let's expand these open. So we're going to have negative 52500 TF plus 525 times 40 will give us 2,100,000, and it's a negative times a negative, so that becomes a positive. 1, 2, 3, yep, equals 3.34 times 10 to the 5 plus 4200 TF. And let's see, if this number is much bigger than this number, so if I do this, take away this and that plus to the other side, we're going to have two positives on either side. Let's do that. So I'm going to have on here 22.1 million. 1, 2, 3, 1, 2, 3. Yes. Take away 3.34 times 10 to the 5. So that'll be around the 300,000 mark, obviously, equals 4,200 TFs plus, because opposite of a negative is a plus, 525,000 of TF, which would equal, let's see, 525, oops, not 525, 529, 200 TFs. Let's do the difference of that. So that's going to be take away 3.34 times 10 to the power of 5 gives me 1766000. We want to get TF all alone, so I'm going to do this divided by this. Should be about in the 3s, so TF will equal 1766000 divided by 529,200. 529,200 gives me about 3.3 degrees Celsius. So that ice, let's see, just double check our answer. That was question 17, wasn't it? 31 degrees. Okay, so I've obviously made a calculation mistake there somewhere, and unfortunately sometimes that happens. Let's double check, see if I can spot it quickly. Yep, half of that. 52,500 times 40, 2.1 million. Here's where I made a mistake. I added an extra 0. That was a bit silly of me. So when I moved that over, I massively inflated this side. Okay. So let's do that calculation again, now that I've got the right numbers there. 176, 6, and 2, 3, divided by 5, 2, well, that's going to change that completely as well there, isn't it? So that will no longer be, that'll be 5, 6, 700. So let's change that as well. 5, 6, 700. 700 gives me 31.1 degrees Celsius, which is the correct answer from the textbook. So we can see that you can do it all in one step. It's about the same amount of math, but you have a few more things to keep track of, which can make it harder. If your algebra is not strong and you're feeling it a little bit careful, do it by the step-by-step. Now I'm going to write out how I would do this step-by-step. I'm not going to solve it. Do it in your own time. So the first thing I would do is I would use Q equals ml to melt ice, and Q equals step 2 from that, Q equals mc delta T to cool the water. Okay, and these Q's would be equal to each other. Okay, then step 3, delta Q, so the loss of energy on the water would equal the gain of energy on the, say, 0 degree water. Okay, this one would have a different temperature. It would not be 40 degrees because we've cooled it down from here, and then you could use some thermal equilibrium. To link these two together. It's going to be about the same total amount of math, but less things to lose track of, so it could be worthwhile in terms of doing that if that's your preferred method. Okay, let's go through to question 18. Now, question 18, 19, a couple of written type ones. Let's have a look at this. A few years ago, it was not uncommon to see cars travelling in country areas with porous water bags made of canvas attached to the front of the car. Why was the temperature of the water in these bags cooler than that of air? Interesting question. If we scroll back up, we are right above this idea of evaporation. Okay, so if we think about what evaporation means that you've given some extra energy in order to cause a phase change. Okay? Well, now, the way we've modelled these questions is that before here is that we say, oh, it all heats up to 100 degrees, and then it all starts to boil all at once. Or the copper heats up to its boiling point, its melting point, and then it all phase changes all at once. In reality, that isn't what happens. And if you've ever cooked any pasta at home or some rice at home, and you've seen a pot of boiling water, you can see that there is steam coming off it before the rest of the water actually even physically boils, because not everything hits boiling point at not every particle hits boiling point at the exact same point. So if I've got this car here, this engine in front of it, if I've got this big bag of water and it's exposed to the air, some of that this water is going to be evaporating into the air, and because it's evaporating, it's taking away energy. And if it's taking away energy, then it must be colder than the thing it is around. In this case, so it's gaining energy from the air, and so it's cooler than the air. And secondly, it's gaining energy from the engine, and so it'll be cooling down the engine as well. But those particles are evaporating. Okay? They're not going to stay at a constant 100 degrees. If it hits that point, it's boiling and the car tends to stop working. But the big idea is the idea of evaporation takes energy. Therefore, delta T lowers, because it's going to lose some, it's going to take that energy away, it's going to be not as hot. There's a really dumb example of it called a salt challenge, where kids will put salt on their hands and then an ice cube on it, and because the salt lowers the melting point, some of the ice turns into liquid, but the rest of the ice near that area with the salt drops in temperature, and so it ends up giving a freezer burn onto your hand. It is not a particularly intelligent thing to do. Question 19. Why does your skin feel cool after placing an alcohol-based aftershave or perfume on it? Same thing. Alcohol has a very low evaporation point compared to water, and so it evaporates even quicker than water. Okay, and so let's just write that the answer is evaporation. Okay, lower BP. Okay. Probably needs less energy as well, but that's not as much important. This is more evident if you're in a breeze or you blow on it. Yep, again, because you are encouraging more particles to evaporate, and so they're gaining energy, or they're taking energy from whatever they're in contact with, and off they go. Is this related to the pain relief spray used by footballers? I don't know. I'm going to quickly give it a quick search. Pain relief spray sports. How does it work? Seems to be this sort of same idea. So it's a cold spray by adding let's see, aerosol spray, magic spray, okay, spray. Okay, so it seems to be sort of a idea. It is possibly numbing an area, so there might be a little bit of nerve thing, but also cooling down the area. And so, well, if you're cooling down the area, it's reducing inflammation, it's making it less painful. Okay, so those sort of things, it's using that principle of thermal evaporation that we can see right above it. So have a read through 10.9 to help sort of wrap your head around that. Thanks very much for listening. I hope your questions are going well. Remember, keep working on it every day. Have a good one, guys.